Hello. So I like also to start by thanking to the organizer for inviting me here to give a talk. And since we are at a summer school and entanglement is one of the topics presented here, I thought that it would be nice to give you an overview about the entanglement detection in quantum information theory, and also to focus on the random matrix approach to this subject. So my talk is going to be at the intersection between quantum information theory and random matrix theory. I will recall some basic facts and also some results that we had within this framework. So I will start with some basic notion from quantum information theory, and then I will devote a part to introduce some entanglement criteria like PPT, realignment, the one that are interested. I also present briefly some a criteria which is based on tensor norm, and this result is from 2022. And then I will give an overview about the random matrix techniques used in the entanglement detection. And here I recommend you Professor Benoit Collins and Yone Kita papers from 2016, where they do an overview, a general presentation of the random matrix technique in quantum information theory, and I will focus mostly on entanglement thresholds. So, sorry, I don't know how to, maybe I could use does anyone knows how to do such that not to have this kind of no? Okay, so regarding the quantum state, can you help me, please? It would be much convenient. Or maybe just scroll with the, I don't know.
Yeah, no, but there should be a way to put full screen.
Yeah.
Okay, I think I will fail.
It's okay, thanks for trying. Yeah, okay. So we know that the evolution of a quantum system is described as a Schrödinger equation, and we have the state of the state vector of the system. And here we have two kinds of states. We have the pure states, which are described by unit vectors on a complex Hilbert space. And we have also the mixed states, which are actually classical probabilistic mixture of pure quantum states. This the most interesting situation comes when we speak about multipartite systems, because in this case the Hilbert space is actually a product of, so we have a tensor product of two Hilbert spaces in the bipartite case, and here appears the problem of classifying the states in separable and entangled. So separability would mean, for example, that the state can be written as a product of two states, whereas if this not happens, then the state is called entangled. Sometimes it's also important to associate to pure states or to associate the quantum states metric description. So for pure multipartite states, we use the space L2. Here, CD, we speak about finite dimensional spaces, and CD is endowed here with the Euclidean norm. Or for mixed multipartite states, we use the space S1, which means that the metric space is endowed with the trace norm. So these are general facts. The idea is that one of the most studied problems in quantum information theories is about detecting entanglement. Since we know, everybody knows that entanglement is a resource, so we want to detect entangled state. And I have to say that here we have many criteria. So maybe in the last 20 years we have too many criteria, which and there is no general overview about this subject. So anyway, the separability problem has been proven to be of non-polynomial complexity, and most known criteria are necessary and sufficient, but they are not practical. And the one that there are criteria that are easy to compute, but they are or necessary or sufficient. And of course, we know that the most common are PPT and the realignment. And we can identify, from what I was interested to present here, we can identify two ways of studying the entanglement problem. The one is based on positive maps, and within this frame we have PPT and reduction. And there are also approaches related to what are called entanglement criteria based on tensor correlation metrics. There is a group in Torun which has some papers about this, and somehow things are similar with what we have introduced in the frame of entanglement tester in the papers from 2020. So just to recall, so separability criteria based on positive maps approach. Here we have a necessary and sufficient condition for separability. If the state rho phi, which is the identity tensor rho applied to rho AB, is positive, but for any positive map. Of course, we cannot characterize all the positive maps, so for this reason, we have we use the entanglement criteria, which state that if for a given bipartite state rho AB, if the matrix which comes from identity tensor phi applied to rho AB is positive, then the state is entanglement. So we need to choose a positive map here. And the most common choices are transposition, and here we have PPT, the well-known PPT, and the reduction map, which will give the reduction criteria. The PPT criterion here is more given into details. What is interesting is that we have the set of PPT quantum states. So it's the set of the states for which the partial transposition is a positive semi-definite. And its practical form states that if the state is not PPT, then the state is entanglement. Indeed, as we had today, it was mentioned this result by Voronovich. In the case of 2 times 2 or 2 times 3, this is a necessary and sufficient condition. And of course, we have also formulation of a metric formulation of this criteria, given that the fact that the trace of the partial transposition is equal also to 1. So separability will imply that the S1 norm or the trace norm of the partial transpose is equal to 1. Less known or used is a reduction criteria, which comes from 1999, and it states that a state rho AB is separable if the reduced states, which are defined here, are also positive semi-definite. Here I have what is called simultaneous reduction criteria, because in this case we need to, you see, we need to compute the partial trace over the one of the subsystem. So that's why you have two conditions. What is interesting is that in this framework of entanglement criteria, it's very important to establish some relation between the criteria. So this will be one of our issues. And for example, what can be seen is the dimension of the second subsystem is 2, so it is a qubit. Then PPT is equivalent to reduced criteria. But in general, reduction criteria is weaker, and the interest on these criteria is coming from the fact that it is connected to entanglement distillation, so all the states that violate the reduction criteria are distillable. Here we have a picture which presents some of the sets that are presented. So in the center we have the set of separable states, and we have PPT and reduction. I said reduction is weaker, and on the right hand side we have the realignment, which we'll see that it's a complementary criteria respect to PPT. So here we have the statement of the realignment criteria introduced in 2003. This criteria has only a metric description, so rho is separable than the realigned matrix, and computing the trace norm of this is smaller or equal to 1. So we have a simple and operational computable criteria. It's complementary to PPT, and it seems that it can be put into, or it can be set in one of frameworks of these criteria, which are based on tensor norm, because as I've told you, we have introduced in 2020 an criteria, an entanglement criteria, which is based on some tester. Here there is a framework on which the entanglement tester theory is based on. So we need to associate some set of matrices, and we define a linear map which transforms actually a matrix in a vector. Here you see we have the entries of this vector are a correlation between Ek and X. We call it entanglement tester if the norm from S1 to L2 is equal to 1. And indeed, this kind of framework works like a local contraction, because the entanglement criteria is presented here. So we need actually, this entanglement criteria has the advantage of possibility to include many subsystems. And what we need to do actually is to compute, so to consider for each system a linear map, as I presented an entanglement tester, and then compute the tensor product of E1, EM to apply to rho to compute what is called projective tensor norm. And if this output is larger than 1, then the state is entangled. So this theory has the advantage that, as I will show you, include the realignment, but also include other criteria. So we can say that the theory can be extended for the realignment case, and in the realignment case, the theory is quite simple, because the set of the matrices that we start with is some matrix operators, basis. And it seems also that this class of criteria introduced by the group from Torun includes can be included in this theory, but actually what they have shown here is that there is a large class of criteria that can be framed in terms of the correlation tensor criteria. As we see, we have realignment, we have also a SIG criterion. This is based on the SIG POVM and many other criteria which are, as I've told you, there we have a lot of criteria. The idea is that since we have so many criteria, it's important to choose the right one, or to choose the simple one. And again appears this problem of classifying the entanglement, the methods that we have. For example, we show in this paper that I recommend you, we show you that using techniques that are coming from operator theory, we can establish, we can compare two criteria, the one that is based on, so the realignment, and the one that is based on SIG POVMs. The question about these two criteria appeared in 2018, and it was a conjecture that was proven or that was based on some numerical evidence. So it was saying that if the realignment detects the state as entanglement, then also the SIG POVM criteria will detect it as entanglement. And actually, it was possible to show using the theory that I based on entanglement tester, it was possible to show that this conjecture is true. So this is based on the inequality that we have here. Of course, that we cannot have this kind of equality for any criteria or for any two criteria, and we would like to have a sort of a table where to compare these tools that we have. And here comes actually the techniques that are coming from random matrix theory, because random matrix theory can offer us some intuition about, for example, the volume of different sets. So again, we have this picture where we have the set of separable states, the set of PPT, red, and realignment, because the most part of the theory has been done for this criteria, as far as I know. So questions about the volume of this set. Here we have this nice result, which comes back from 2002 of Gurvitz and Barum, that states that the largest Euclidean ball that can center it in the maximum mixed state that is contained in the set of the density is separable, and here they computed the radius of this ball. Of course, that this cannot give us so much information, but still we understand that we can put a ball inside a separable set. The problem of determining the volume of different sets can be stated equivalent to that of computing the probability that a random quantum state belongs to a given set. And here I've presented, since I was speaking here about random quantum states, I have presented also which are the probability distribution on the set of quantum states. So if we speak about random pure quantum states, as I presented before, they are vectors, unit vectors, and if we consider to be uniformly distributed on the unit sphere, then we said that we have a random pure state that follows a uniform distribution. Whereas for the part related to random mixed quantum states, then we need here to consider two positive integers, d and s, and a random pure quantum state, x, that is from CD tensor CS, and the distribution of the state, which actually traces out the second subsystem, the environment, This is called the induced measure of parameters DNS. This result has been presented in the papers that are mentioned here. So the idea is that if we want to simulate on a quantum computer a random quantum state, then we need to consider rho to be G star over the normalized. This is actually a Wishart matrix. And I like here to present the concept of threshold for entanglement criteria. So given a random mixed quantum state, the phenomenon of a threshold states that if the size of the environment scales linearly with the size of the system, there exists a threshold value such that for any C which is smaller than this value, then the probability that the state satisfies the entanglement criteria vanish, so it's equal to 0. Whereas for all C that are larger than this value, then the probability that the state satisfy the entanglement criterion is 1. This concept has been introduced in 2012 and has been calculated for partial transposition by Guillaume. And actually here I have collected one of the some results related to the computation of thresholds for different entanglement criteria. So as I announced, we have PPT criterion by Guillaume in 2012, and then for some regimes also in 2013 by Jon and Theo Bănică. Then we have a reduction criteria which we took care in 2014 and 2015. Then, of course, that there have been other approaches related to these criteria that are coming from positive maps. Realignment criteria, the threshold for realignment criteria was established in 2012, and there is another criteria called R extendability, and this work belongs to Cecilia Lancien in 2015. So all the results that are in the framework of thresholds for entanglement criteria, and we need also to mention the result for separable states from 2014. Here there are nice results related to the set of separable states. So, for example, in the case that when the system and the environment have the same dimension, we can, it was established that the ratio between the volume of the separable states and the one of the density matrix vanishes. So, of course, the SEP is much smaller. And for S going to infinity and AK fixed, the set of separable states concentrate around the maximum mixed states. And here are presented the results for separable states. So we don't have here a threshold result, since the theorem states that there exists these constants, which and the function such that we can have results like thresholds, but we cannot compute the threshold because we need to get rid of that logarithm that appears. So this is, I think, no problem as far as I understood. Since I needed to go also in some details related to the threshold, I thought that it would be nice to present the threshold for reduced states. And you will see, maybe not into too many technical details, but rather present an algorithm how we can find these points, these threshold that establish, let's say, a phase transition between belonging to a certain set and we use, of course, the Wishart matrices of parameter D and S, normalize, and for example, in the case of the reduction criteria, we need to compute the reduce matrix of the Wishart. So it is written here below, and we would like to study the distribution of the eigenvalue of this matrix and evaluate the probability that R is positive semi-definite, because the reduction criteria, this is what is required. Separability will imply that this matrix is positive semi-definite. Here appears what was presented in the morning. So indeed, because we want to understand the empirical eigenvalue distribution, we need to compute the moment of this random matrix R, so the reduced matrix. And you see, we need to compute actually the powers of R, which means to be careful how to make this kind of factorization between the M copies of the matrix R. And the result presented in equation 4 is expressed in terms of the parameter S, N, and K. So we need a lot of combinatorial work here. But the best part is coming from the fact that we can always use this graphical representation. For example, for the matrix R, which is X times X star. Well, this is the graphical representation where we have here the partial trace, tensor identity minus the matrix. So this is the graphical representation. And for example, the first two moments are presented by equation 5 and 6. And we need to understand how they behave when we consider the following asymptotic regimes. So we have, for example, what is called the balance asymptotic, which means that both n and k goes to infinity, but k over n goes to t, s goes to infinity, and we have s over n, k go to this c, a constant c. Unbalanced asymptotic is necessary because in the case of this criteria, it's important to understand where you trace, you compute the partial trace. And for example, the balance case and as well as the unbalanced first case did not produce results because all the quantum states satisfy the simultaneous reduction criteria. But we have a result, so we were able to compute the threshold point in the case of unbalanced asymptotic second case. So here, using techniques that are coming from free probability, we can state that the empirical eigenvalue distribution of the normalized reduced matrix converge to a compound free Poisson distribution. And this will help us, for example, to understand and to study the support positivity, because we want to understand where the eigenvalues are positive. So, for example, here in this for this compound free Poisson measure, the support is contained in is positive if and only if C is larger than C red, which is here written. So this kind of algorithms will help us, for example, to compute the threshold point. So we said that for all C that are smaller than the point that we found, the value that we found the probability that the random states satisfy reduction criteria is 0, whereas for C larger than this point, the probability that the states satisfy reduction criteria converges to 1. And here we have stated in a sort of theorem the result related to the threshold for the reduced criteria. And we have set a sort of a table where to compare all these results, to collect them and to compare. And for example, for PPT, we have the value 4 here. The realignment is 0.72, and the reduction is 0. So for some cases, we are able to recover well-known results. So for example, if K is 2, we set that the two criteria, PPT and reduction, are equivalent, and also the values for the threshold are the same. As you see, CPPT, so the threshold for the PPT is larger than the one for reduce. So again, we agree with the theory. And what can be seen that in general, the threshold for separable states it's larger. So this means that this set is smaller respect to the set of PPT and all the others criteria. The last slide are related to the fact that this kind of theory has been also studied in the framework of absolute separable states. So absolute separability means that we define this set A set. So we have the states rho for which the conditions are expressed in terms of the eigenvalues. And we see that inside of the A SEP there is a SEP ball. Then we have also A PPT and A reduce, which can be defined in a similar way. There are also results related to, so there are an analytical result related to the description of this set. So we have, for example, one of the most known description related to APPT in Hildebrand in 2007. The thresholds for APPT and A red has been also found. And one of the conjectures that I think, as far as I know, is still open is related to the fact that ASAP is equal to APPT. And some evidence have been also presented in some papers related to this conjecture of the equivalent between the two sets. Again, using the same algorithm for computing the thresholds, we have a threshold for A entanglement criteria. So here are presented only APPT and A red, because as far as I know, A realignment is still an open problem. So going back to what I have presented, so my aim was actually to give you an overview about the entanglement criteria and to show that so there are classical approaches for understanding from the analytical point of view how to characterize this set APPT red realignment, but the main concern is about, of course, separable state. I also wanted to attract your attention to this criteria, this class of criteria which are based on correlation tensor and entanglement tester, and also to show you that we have tools from random matrix theory in order to understand or to have an intuition about the volume of this set, and maybe to attract your attention also to see if other threshold and other information about entanglement criteria can be computed for this new class that are now presented, recently introduced. So that was all, and thank you.
Your questions? Comments? About this kind of entanglement, does it require positivity of the maps or not? Positivity.
So we
of the maps E.
Yes.
Or the density matrices related. Are they required to be positive or not?
The map phi, yes. So the entanglement criteria based on positive map.
E. The map E.
E.
Are they required to be positive?
Yes. So the map phi, the one identity tensor phi applied to rho, has to be positive. Yes.
Is there an entropic interpretation of this entanglement? Because it's new for me. Like, is there a characterization using entropy?
For the entanglement?
For this entanglement?
No, there is not. So I think you asked me about the criteria based on tensor on entanglement tester, no? The one, the positivity. Maybe I did not get the question. So just a minute. So if your question regards this criteria, we don't require map to be positive. This is just a linear map, introduce it here. So we require the norm to be equal to 1 in order to be an entanglement tester. Here, when we speak about this criteria based on positive maps, here we have the map to be positive. Okay. And related to the question of the entropy, you said?
Because often the entanglement is a point and the field is characterized often by entropy as a measure of entropy.
So we don't have this kind of approach.
Maybe I have one. So in all your random models, the measure is fixed. Can we introduce dynamics on that? Some process that's interpoled with?
I think so, but I wouldn't know to say too much about this, but maybe yes.
Nobody has studied it.
As far as I know, no. But maybe Guillaume knows better about this kind of threshold. If there were already more than I presented here, there are any other relevant results. As far as I know, these are the only one.
I don't know. So I will give some elements of proof to this theorem later this week.
Ah, very good.